Now we will discuss space-time and the twin paradox. But what is space-time? What is space? So far, we are familiar with 3D space, x, y, z, and plus time. So, we are in four-dimensional space-time. In order to see the 3D along the corners of our room is quite easy, but the dimension of time is what we cannot see. But we know that time flows only in one direction. Suppose I am standing on the rooftop of my house. With respect to me, of course, I am not changing the position. And with respect to someone beside me or in some other building who is looking at me, also concludes that I am not changing my position. So this relative position is fixed in space, but time flies. My clock will tick continuously. And for simplicity, we are not considering y and z dimensions, we are considering only x. But one thing we know very well, that we cannot go backward like this, because if we go backward like this space is okay, because in this space we can go forward, backward, upward, downward, or sideways. But in time we cannot go backward. Let's consider the space-time plot. Here I will plot the space axis and here I will plot the time axis. So here the space increases, it can decrease of course, but time will increase only in one direction. Suppose I consider this much amount of distance, which is equivalent to 1 light year, that is the distance travelled by light in 1 earth year. And this is, suppose this point correspond to 1 year in time, and this straight line making an angle 45 degree, this represents the constant speed of light. That should be 45 because tan 45 is equal to 1. If we look into the space-time plot, we can see that we cannot play in this section. We cannot go like this. I mean, the area which is under this C straight line, this area cannot be achieved by us, because the speed, we cannot travel with the speed which is higher than the speed of light. But we can travel in this region, because here my speed is always less than c. So this region staying at the Q point is not allowed, but this region is allowed. Let's come to the twin paradox. Suppose on earth two brothers or two sisters, or maybe one brother, one sister, a pair of twin is there, and there is a spaceship which, when flies by our earth, takes this twin, this one, along with it, and it travels with a speed of v equal to 3 by 5 into c, and it travels earth year of 5 years, and then again it stops here, it comes back with the same speed 3 by 5 c, it travels another 5 years according to the clock on earth. We know in 1 year light travels a distance which is called 1 light year. So in 5 years light travels a distance which is, this is speed, this is time, we know s equal to vt, distance equal to speed into time. 3 by 5c is the speed and this is the time, so it's 5 light year. Return journey is also of 3 light years of distance. So if we plot the space time plot for both of them, both the twin who is residing on earth, for him the time elapsed is 10 years. But the twin who is in the spaceship first goes up to a distance of 3 light year, then again comes back with a distance of 3 light years. If we think about the two parallel mirrors separated at a distance d within a spaceship, so if light starts from this down mirror and then it reaches the upward mirror, this upper mirror, then obviously the time taken by light is t equal to d by c, because c is the speed of light. According to the observer inside the spaceship, the light moves vertically, and this is the time measured by observer inside the spaceship. But what about the observer who is residing on earth? According to him or her, the light will move like this. I have discussed this in my previous video. As the spaceship is moving, so he cannot perceive the upward and downward, that is the vertical motion of light cannot be perceived by the observer on earth. He or she will see the light is moving like this, first this and this. So the time calculated or measured by this observer is obviously greater than this time, because here it is moving vertically upward and downward, but here it is taking a little bit longer path, hence a little bit longer time. Suppose the time calculated by him or her is t prime. So here is the scenario. This is the first mirror, the distance between them is d. This is the upward motion as seen by the observer on the spaceship, but the observer on earth will see that the light is going like this. Suppose this distance is d and this is d prime. This is obviously d, and this distance is vt prime, because the relative speed between the spaceship and the observer on earth is v. So by the time t prime, according to the observer on earth, the spaceship has moved a distance of v equal to t prime. Hence, the Pythagoras theorem will tell us d prime square equal to d square plus v square t prime square. We'll put d prime equal to ct prime and d equal to ct. So here is the calculation. Here are the steps. I have just substituted for d and d prime. We have found that t equal to t prime into root over 1 minus v square by c square. It is quite evident from this relation that t prime is obviously greater than t. Let me recall, this is also discussed in my previous video of special theory of relativity. This quantity is called the Lorentz transformation, because this is acting like a bridge between the two frames, two times measured by two different observers. Now, for example, the spaceship is moving with a speed of 3/5 of the speed of light. So if I put 3 by 5c here, I will get t equal to t prime into 4 by 5, which gives me 4 t prime by 5. So from this we can see that t prime is obviously greater than t, which means if, now what does this relationship tell us? If the observer on Earth measures 5 seconds, then the observer on spaceship will measure the same interval as 4 seconds. Just let me tell you once more that this straight line, the 45, making an angle 45 degree with the t-axis, it is actually represents the speed of light. Now this is the space-time plot for the twins. According to the twin on Earth, 10 years have been elapsed. According to the twin, it is not 10 years. Let me see why. These lines are the speed of light. Now suppose they have 2 clocks, and when the clock with the twin inside the spaceship sends a signal, it reaches to the observer, reaches to the twin on Earth, but definitely that information needs some time to go. It is not like that if someone stands here at the spaceship, he or she sends a signal and that signal instantaneously reaches this person on Earth. That is absolutely not possible. The signal must have some time to reach. So let me take, for example, that these two brothers or sisters, they have these two twins, they have a radio frequency kind of signal. So when he is 2 years old, he sends a signal and it reaches his twin in the spaceship. But that takes a finite time. The instantaneous transmission of the signal is not possible because the information cannot travel greater than the speed of light. Now suppose when the brother or sister is of 2 years old on Earth, that twin sends a signal to this twin who is on the spaceship. So here he is. What will be the age of this twin? If I draw a perpendicular line, so this corresponds to this time, not 1 year, just slightly above. So it's like a 1.25. Actually, I have done it on a graph paper. That's why I know the measurements already. You can check it. You can verify with in yourself actually. So here, if we can see that Earth year, the age of the twin on Earth is now of age 2 years, and the corresponding time when that signal, that he sends a signal that now I am 2 years old, that signal reaches the twin on spaceship, that time corresponds to 1.25 years on Earth. And as it is traveling with the speed of 3 by 5c, we have already calculated that t equal to t prime 4/5. So on spaceship, the conversion factor will be 4/5. So now the spaceship the twin on inside the spaceship, I'm sorry for fumbling, the twin inside the spaceship is of age 1 year. What if the twin residing on Earth is of age 4 years? This is 2.5 years approximately. So on Earth, this point corresponds to 2.5 years. So on spaceship, the age of the twin is 2.5 into 4 by 5, which is equal to 2 years. Similarly, when it is 9 years, the twin on Earth sends a signal that I am now 9 years old. This signal reaches the twins into the spaceship. That time corresponds to on Earth is 7.75 years. So on spaceship, the age of that twin is almost 6 years. So here is a list of comparison. When the twin on Earth is 2 years, twin on spaceship is 1 year. When the twin on Earth is 8 years old, the twin on spaceship is 4 years old, and so on. You can just multiply with the conversion factor 4 by 5. Here in this case, not always of course, because here u is equal to 3 by 5c. And when it is 10 years for the twin on Earth, the twin on spaceship, inside the spaceship, will have age 8 years. So they cannot reunite on their 10th birthday because the twin on Earth is now 8 years old. But what if the spacecraft travels with a speed greater than 3 by 5c? Suppose the twin is traveling inside the spaceship with a speed of 4 by 5c. The spacecraft is moving with the speed of 4 by 5c. Then the twin inside the spacecraft will be even younger, because then the spacecraft clock will be slower even more. Here is one thing I would like to mention, that when this twin says that your clock is slow, this twin can say that your clock is also slow. But one thing I would like to mention, that this twin on Earth is moving with a constant speed, which is the speed of Earth. But this twin on the spaceship will experience acceleration. Acceleration is something what you can feel suddenly. Suppose you are inside a train. The train starts its journey suddenly and you will be pushed a little backward. You can feel that there is acceleration. So here the twin inside the spaceship will experience acceleration at first here when he or she, that is the spaceship, starts its journey from Earth. At the point of return, again it gets slowed. It eventually stops here. Again it accelerates and then it reaches Earth. Here it will again have retardation because it needs to stop there. So he is in an accelerating frame of reference. And that acceleration, Einstein said, makes this clock slower. And as that frame of reference inside the spacecraft is equivalent, according to the equivalence principle, to the reference frame on Earth. So if something is moving with the speed of, is having an acceleration of g, so his or her clock will be slower also. So in a spacecraft which is accelerating, for this observer, who is in an accelerating spacecraft, it's very difficult for him or her to calculate the time of a clock on Earth, because he is moving with acceleration. And if he is moving with acceleration, we can't apply, we need to apply general theory of relativity then. Suppose here is an observer on Earth, here is an observer in a spacecraft. First, for 10 years, this observer is moving with the spacecraft with acceleration g. Then after 10 years, the spacecraft gets slower. So it is now traveling with a retardation. That's why I have written this as minus g. The value of the retardation is g. And he travels with this retardation with another 10 years. Then after this 10 plus 10, 20 years, he returns back. In the first phase of his journey, he accelerates for 10 years with an acceleration plus g. Then in the midpoint, he decelerates with the retardation value of minus g. And he travels for another 10 years and then comes back to Earth and rejoins them. This is the time calculated by him, by himself. That is, who is inside the spacecraft. But what about the time, according to him, going on Earth? There is a book of Cox and Forsaw. You can consult that. There the calculation has been done. I am just writing you the result. So after doing the calculations, the Earth clock, the time on Earth has traveled already for 59,000 years. So when he returns back he returns back after 20 plus 20, that is 40 years. 59,000 years of Earth would have been gone. So accelerating reference frames makes clocks slower. And if this is valid, the acceleration in the reference frame makes the clock slower. So from the equivalence principle, this accelerating reference frame will experience a slower clock, and according to the equivalence principle, the same thing will be applicable on Earth, because on Earth we are experiencing gravitational field, and in presence of the gravitational field, clocks get slower. So if we are in a high-rise building, who is on ground floor and who is on top floor, what about the clocks? The clock ticking at a slower rate here, because here the effect of gravity is slightly greater than here on the person who is on the top floor. But that not much. For a whole lifetime, this clock will run slower by a few microseconds only. So that is quite insignificant for a whole lifetime. But at least when you are on the ground floor you are living in a ground floor of a very high-rise building, you must have that your clocks are running slower than the person who is on top of the floor.